Thank you for joining to watch our second video on our course on laser physics, and now the topic is about the laser idea. So we want to now unravel to you the main ingredients we need for a laser to start lasing. So if you look at the kind of physics and the mathematics, what we do have here is that the laser operation in principle is very simple, and we can divide that into three main steps or phenomena that need to take place so that we can have a laser built and performing. So let's first look at the first step. So what we need is that we need to achieve light amplification in the active medium or gain medium via stimulated emission process, as we already discussed in the previous lecture. What is a stimulated emission process? In addition to that, we need to introduce a feedback mechanism that really helps sustaining the amplification. And in the terminology of laser physics, we call this kind of amplification or lasing as an oscillation of the system. Achieved using an optical cavity. So this is how we realize feedback mechanism in practice. So we place a gain medium inside an optical resonator, and that's where we get the feedback. And the optical cavity also introduces losses. So that's also the kind of in a way downside or a feature of a laser resonator that needs to be battled and managed and engineered to really realize lasers. That's the second mechanism or step we need. And then finally, what we need to some kind of mechanism to supply energy into the active medium, into the gain medium. So basically that's a pumping mechanism, and we need that to really exceed the lasing threshold to realize population inversion in the electron states so that the gain medium can start lasing or oscillating. Next, we will briefly explain the different steps or functions and the governing main principles to you so that you understand what will follow in the course. So first, let's look at light amplification. So that's the first key aspect of making a laser. And the main point here is that we want to realize amplification taking place due to having an active medium inside our resonator. An active word here just means that it's the gain medium that we are dealing with. Let's start by considering a photon flux denoted with letter F that's interacting with the active medium, and the beam has a cross-section denoted with S. So that's the laser beam hitting our gain medium. Now let's look into the change of number of photons over time, and that will be proportional to the change of the photon flux F due to active medium. So essentially, mathematically put, we are looking at number of photons per unit time that is proportional now to the beam cross-section S times a differential change of the photon flux dF. We do not concern here non-radiative decay processes. Neither do we concern spontaneous emission processes because they do not affect the photon flux. So non-radiative decay processes do not emit photons, or rather, specifically put, they do not emit photons that result in photons operating in the lasing mode. So we do have, of course, ultimately, usually also photons emitted by non-radiative decay mechanisms, but those photons are either directed into a different direction where we actually do have the lasing beam formed, or the wavelength is different so that it doesn't really participate into the oscillation, so into the lasing action. So that's what's meant here. So that even though pedantically speaking, we could say that of course every non-radiative decay process usually ends up also some emission of photons, we in terms of laser physics, say that those photons are not of our interest because they do not contribute into the formation of lasing beam. So that's why we say that there's no such photons due to non-radiative decay. Then the other process of interest or not so interest is the spontaneous emission, and this emits photons in random directions. And here the key is this wording, random directions. So these spontaneously emitted photons don't really contribute much into the lasing beam, and that's why we do not consider them in what follows. Now, only absorption and stimulated emission thus are processes that contribute to the change of the photon flux, so dF. So we can write that the S, the cross-section of the beam, times dF equals the time derivative of a ground state N1, so that's the absorption process, times S times ds, so kind of like differential thickness of our gain medium upon which the beam is propagating, and then we have another contribution into the changing flux due to a stimulated emission, so that would be the time derivative of the excited state population N2 with respect to time times the beam cross-section S times the ds differential length scale. So this S times ds is essentially V, the infinitesimal volume, concerning this description, and we can use this rate equation or we can use the rate equations that we discovered in the previous lecture to write this simply as a photon flux F times N2 times S times dz minus photon flux F times N1, the population of the ground state, times S times ds, or put together F times N2 minus N1 times S times ds. So that's the mathematics here. Let's proceed. So we can simplify this equation so that we can write a differential like this. So the kind of change of photon flux with respect to propagation, and that would be equal to photon flux times N2 minus G2 divided over G1 times N1. Here G1 and G2 are the degeneracy factors of these states. So we may have like degenerate states, and that's the kind of factor taking into account that kind of physics, but usually we do not really need to be dealing with these kind of factors in this course. For amplification, what we need is that the photon flux, of course, must increase. So mathematically, what must take place is that this photon flux derivative with respect to propagation length z must be greater than 0. That's mathematically what we are searching for. And then this gives us the condition for light amplification. And that would be so that the N2, the population of the excited state, must be greater than the G2 divided by G1 times N1. So when this condition is being met, what happens is that now stimulated emission processes would dominate, and that would mean that the medium, the gain medium, actually would act as an optical amplifier. And if this condition is not met, what happens is that the absorption processes dominate, and then basically the medium acts like an absorber. So these are the two different scenarios out there, depending on whether or not this condition for amplification is being met. Let's now look when we could possibly meet or fulfill this condition and where we cannot fulfill this condition. So let's look first at a situation when we do have the gain medium at thermal equilibrium. So now in this case, the ground state is more populated than the excited state due to the fact that the thermal equilibrium takes place within that system. And this is basically arising from the fact that the system resides in the minimum energy state, macroscopic state, and that's it. And that's what we have in thermal equilibrium. So the population distribution at equilibrium basically is governed by the Boltzmann distribution. So each of these populations, N1 and N2, they would be proportional to the degeneracy factor Gn, and then the exponent of E minus En divided by Boltzmann constant Kb times the temperature of our system. So here basically Nn is the population of our state in N, Gn is the degeneracy factor of state N, En is the energy of this state, and Kb is the Boltzmann factor or Boltzmann constant, and T is the temperature in kelvins. So this is the basic classical thermodynamics. Now, what we do have for the ratio of the excited and ground state populations, we can write the population ratio as N2 over N1, and this is approximately G2 divided by G1, and then the exponent of minus E2 minus I1 divided by kBt. And what happens now? The E2 is the higher energy state, so that we have a condition that this ratio is smaller than the degeneracy factor, and thus the amplification condition N2 that it should be larger than G2 divided by G1 times N1 is never met at thermal equilibrium. So what this implies and means is that for any active medium that is in thermal equilibrium, that medium behaves as an absorber and not as an amplifier. So something must be done in order to achieve amplification. So we really must drive the system out of equilibrium, and this is done by having some kind of pumping mechanism that we can strongly excite the ground state, N1 state, or like a E1 state into a higher electron state. And that's how we create a population inversion, and that's how we create a case that the system can act as an amplifier. So let's now plug in some simple calculations to really estimate what happens in terms of thermal equilibrium. And just for the kind of sake of providing some tangible real-world examples, let's consider a neodymium YAG laser. So the energy gap of interest here between the lasing states, E2 minus E1, is basically close to 1.165 electron volts. So in terms of wavelengths, that would be a transition of 1064 nanometers. This is a very often occurring wavelength when we are looking at lasers. And then we are looking at the kind of room temperatures. So now if the T equals 300 kelvins, we get to the ratio of populations, roughly this kind of value, which is extremely small value. So the N2 population is extremely small compared to the ground state population. And basically this means that we don't really have many electrons in the excited state. So this is what happens at equilibrium at room temperature for a realistic system. So even at high temperatures, when we would really go with the temperatures approaching infinity, the best possible outcome would be that the two populations would be equal. And this still condition does not satisfy the lasing condition, so even this is not enough. So something really must be done to change the game. So the conclusion here, as I already said before, amplification of light is impossible at thermal equilibrium, so we must do something else. And we cannot just increase the temperature of the system and hope that that would somehow improve things. So what do we do in practice is that we really need to drive our gain medium out of equilibrium, and this is done by a suitable pumping mechanisms. And this provides a possibility to realize optical amplification. And how do we sustain this amplification and really achieve a stable lasing operation or laser operation or oscillation of the laser? We must have a positive feedback mechanism in the system. And how do we do this in practice is that we put our gain medium inside a cavity or inside a resonator, and typically that kind of resonator is formed by using two mirrors as shown in here in this figure. So this is basically the kind of simplest scenario we can consider. So we have our gain medium, our active medium here. We place that within two mirrors, and when we have a stable resonator formed, lasing beam can start forming here, and then we can start having amplification of light, provided that we are pumping this active medium strongly and so forth. So this is basically what we will be looking at next, what will happen. So let's consider again this photon flux, now F0, at a point P that's shown in that figure, that will be inside the cavity. After one round trip for this beam of light, the flux becomes F equals F0, the original flux, then times 1 minus L int. That would be the internal losses associated with the medium, so basically scattering, absorption, and so forth. Then we have G, that's basically the gain provided by the active medium, and then we have the reflectivities of these two cavity mirrors. Then we also have another gain term for the second pass, and then we have again internal losses times the reflectivity of the first mirror. So this is basically what happens. So here L int is the internal losses arising, for example, from scattering of light, from absorption, and so forth, all these unidealities within our resonator. Then R1, R2 are the reflectivities of the two cavity mirrors, and G is basically the gain provided by the active medium. So now let's look what this implies, what these terms imply. So we start with a given photon flux here at a point P, and we start propagating. And first we propagate through the active medium of length L, and then we are also incorporating the losses here. So this first 1 minus L is basically the losses due to propagation of L int. Then we have gain factor here. So we have a single pass gain factor arising from the fact that the beam is propagating through the gain medium. Then we have reflectivity of the second mirror here. Then we are propagating again. We have a gain factor here. Also the losses through a single beam propagation through the cavity. Then we have a reflectivity of the first mirror here, and then we are returning. So one round trip is being completed, and this is the photon flux afterwards. Now the gain factor G is derived by integrating the photon flux equation. So F is equals F naught, and then on the exponent we have sigma, the cross section, times L, the width of the gain medium, times the population difference. So basically the population inversion, so N2 minus G2 divided by G1 times N1. So that's basically the amplification, the gain factor. So that's what we describe using this F0 G factor here. Here L is the length of the active medium, and then that population difference is basically the means of achieving light amplification. After one full round trip, the photon flux of course becomes, and we can just plug in the numbers that we already have discovered. So this is what we have here, and now we have replaced the gain terms here so that there we have this exponent there arising from the factor that we have 2 times the gain factor this, and here delta n is basically this term here inside the parentheses of the exponent. Now we have defined the population inversion parameter delta n as in above equation, that's the n2 minus the degeneracy factor ratio times n1, so like this. The term 1 minus L int squared times R1 times R2, that's basically the total cavity losses, and exponent 2L delta n is the round trip gain in our equation. So these are the terms that we are interested in. For laser operation, of course, we want that the photon flux increases. So each round trip, the F must be equal than the original photon flux within that point P. So E must be greater than F naught. So basically that gives us a condition so that the losses times gain must be larger than unity. And now we can really define the threshold critical population inversion. So delta NC as in the critical threshold level, that is the case when we have a population inversion that gives rise a possibility that the gain increases. The gain is larger than the losses of the cavity. So basically plugging values into that exponent and solving with respect to delta n, we can write this kind of logarithm term here. So we have the logarithm of R1 plus logarithm of R2, that's the mirror reflectivity, times 2 times the logarithm, the natural logarithm of 1 minus L int, the propagation losses inside the cavity divided by 2L. So now when delta n equals delta NC, the critical population threshold, the gain exactly compensates for the cavity losses. So this is the philosophy how we reached this value for delta NC. And once this threshold is being met, we can start having lasing action. So we can have laser oscillation within that cavity, and this may start happening even from a single spontaneously emitted photon inside the cavity. So now we really start having amplification of light, we have a positive feedback, and we really can have steady amplification of light within the lasing medium. And then a few words about logarithmic losses. So now for the case of critical population inversion, so delta NC, we can really simplify this term by using the concept of logarithmic losses. So let's just define gamma term. So gamma 1 or gamma 2, for example, that would be minus the natural logarithm of the mirror reflectivity. And let's also define gamma I as a minus natural logarithm of this 1 over L int term. And then we can write a total logarithmic loss gamma as a sum of these different contributions of losses. And now we can simply write the threshold critical population inversion value, delta NC, simply as a gamma over 2 times sigma times L. And this equation doesn't really look much. And on the other hand, that's a good portion of physics that when we are able to have some simple equation to look at, then we can really say much about physics. So this is basically a very illustrative equation for us to look now. When we want to achieve a population inversion, so basically we want to have a population inversion or a population difference that is larger than this critical population inversion value, because that's when we have lasing action. So we must have a population that is larger than this ratio. And here we see that the losses are a detrimental factor. So the smaller we can make the losses, the easier it is to reach the value. And then of course, it's the absorption or stimulated emission cross-section that matters here. The kind of smaller we have this, harder it is to reach population inversion and the vice versa. And then of course, the length of the gain medium affects here. So if you can make the gain medium longer, so the gain crystal could be made longer, then it would be easier to reach the population inversion. In practice, and this really helps like forming rules of thumb, the internal losses are very small. Similarly, usually the mirror transmittivities are very small, so T1 and T2 are far smaller values than 1. And these are basically the mirror transmittivities. It's because like the mirror reflectivity R1 equals to 1 minus T1 and so forth. We can now approximate these logarithms by using the Taylor's expansion. So if you take a natural logarithm of 1 minus x, that's basically when x is small value is minus x to a good degree of accuracy. So this takes place when x is smaller than unity. Now we can apply this to the total logarithmic loss, and we can simply write that the total gamma, the total loss is approximately T1 plus T2 plus 2 times L, the total losses of the cavity. So this is the first order approximation for the total logarithmic losses, but it really simplifies the calculations for estimating the threshold conditions of lasing. So this is a really useful piece of an equation to really grasp how the system behaves. So now I think I'm done with my second lecture. I hope you enjoyed, and please stay tuned when we are going next to discuss about the pumping schemes for lasers. Thank you for watching and have a good day.